In previous day we have discussed the DSB-SC double sideband suppressed carrier system to mitigate some problem related to AM, and wastage of power was the basic problem that was taken care of in DSB-SC. But still there are a lot of things that we can improve. In double sideband we used to send both the sidebands, but one sideband is sufficient to produce the baseband signal. Not only that, the bandwidth requirement of DSB-SC is same as that of the amplitude modulated signal, so we don't have any advantage as far bandwidth is concerned. So we have to address these two things. One is the bandwidth, second is we have to reduce the wastage of power more. So the next option or the next type of modulation is called the single sideband suppressed carrier system, where instead of transmitting both the sidebands, we will transmit only one sideband, either upper sideband or lower sideband, so that the power will go, or the total transmitted power will contain the information, and the bandwidth requirement must be as small as the baseband signal. So let us see how this SSB-SC works. If we assume that x omega is the spectrum of the baseband signal, and we are assuming the spectrum is like this, it is a band limited signal with maximum frequency of omega m. Now for DSB-SC, the spectrum will be shifted by an amount fc, that means by an amount omega c in positive direction and negative direction. We have seen it earlier in previous class when we were discussing the basic principle of DSB-SC. So this is the spectrum for DSB-SC. Now what we are doing, this section is the upper sideband and this section is the lower sideband, and both the sidebands are carrying equal amount of information, and DSB-SC used to transmit both the sidebands. So in this new technique of single sideband suppressed carrier system, we will transmit any one of the sidebands, like this one. Here the lower sideband is suppressed and we are allowing only the upper sideband to transmit, or we can suppress the upper sideband and we can transmit only the lower sideband. Now if you observe the frequency range of SSB-SC, say for this case where upper sideband retains and we have suppressed the lower sideband, the frequency components present in that particular signal is from omega c to omega c plus omega m. That means this bandwidth is omega m only. In terms of linear frequency, it is fm, because omega m equal to 2 pi fm. So bandwidth requirement for this SSB-SC becomes fm hertz, where fm hertz is the bandwidth of the given baseband signal. 0 to omega m means in linear frequency domain we can write it as 0 to fm hertz. So this SSB-SC is the ultimate solution for as per disadvantages of AM is concerned. Because first of all, wastage of power is absolutely zero. Since we are sending only one sideband, so all the power is going to the only one sideband. At the same time, the bandwidth problem, that means enhancement of bandwidth, is now reduced. So now bandwidth becomes same as that of the baseband signal. Now to understand this SSB-SC properly, what we do, we first try to understand the single tone SSB-SC. So first, x omega is assumed to be single tone, that means it should contain only one frequency. That means it is a sinusoidal wave at frequency of omega m. So we will get, if we consider the spectrum of the baseband signal is a spike at frequency omega m and minus omega m. So if we use this x omega to produce double sideband, then we should get two spikes at frequency omega c plus omega m and omega c minus omega m centered at omega c. There should not be any carrier because it is double sideband suppressed carrier system. Similarly for negative frequency. Now if we want to suppress the upper sideband, then this spike will be suppressed and only omega c minus omega m component will be there. So this is the situation when we keep lower sideband. Similarly, if we keep the upper sideband, then only omega c plus omega m component will be there in the spectrum. So this one is the upper sideband and lower sideband is suppressed. So this is the spectrum of single tone single sideband modulation scheme. So we can write xt it is the baseband signal, xt equal to cos of omega m t. For the sake of simplicity, we have omitted the amplitude part. So SSB-SC signal with LSB lower sideband, and in our previous spectrum, if you see this spectrum, if we keep lower sideband, the only existing component is omega c minus omega m, and it is a spike, that means it is a cosine wave. So for LSB, the single sideband suppressed carrier system, the only existing component is cos of omega c minus omega m into t. So SSB signal can be written as cos of omega c minus omega m into t. That can be written as cos of omega m t cos of omega c t plus sin omega m t sin omega c t. Similarly, if we have SSB-SC with upper sideband, SSB-SC with upper sideband, then from the spectrum we can see that instead of frequency omega c minus omega m, we should get a spike at frequency omega c plus omega m. So SSB-SC with upper sideband can be written as cos of omega c plus omega m t, that can be written as cos of omega mt cos of omega ct minus sin omega mt sin omega c t. So if we combine these two expressions, we can write the expression for SSB as cos omega mt cos omega ct plus minus sin omega mt sin omega ct, and this plus sign is for lower side band and minus sign is for upper side band. The sine terms may be obtained using the corresponding cosine terms simply by giving a phase shift of minus pi by 2. So we can write sine of omega ct is actually cos of omega ct minus pi by 2. Similarly, sine of omega mt, that is equal to cos of omega mt minus pi by 2. Now if we want to make a general expression, or if we want to write a general expression for SSB-SC, then this cos omega mt was our original message signal, and here we have sin omega mt in the expression, and we are getting sin omega mt from cos omega mt by a minus pi by 2 phase shift, minus pi by 2 phase shift. So now if I want to make it general, that means instead of writing cos omega mt, if we write say xt equal to cos omega mt for this case, now for single tone xt equal to cos omega mt. Now if xt is no more single tone, it is a general arbitrary signal, under this condition how we can write this one? See, sin omega mt is obtained by changing the phase by minus pi by 2, so this particular coefficient can be obtained by changing the phase of the baseband signal, exactly by minus pi by 2, all the frequency components of xt must be changed by minus pi by 2 to get this part. So we can write is SSB equal to general expression cos omega ct plus minus xht sin omega ct. This xht is obtained by changing all frequency component of xt by minus pi by 2. This xht is called the Hilbert transform of xt. Hilbert transform of xt. So let us try to understand the Hilbert transform. Hilbert transform is defined in this way: xht equal to 1 by pi xt convolution of 1 by t, that is equal to 1 by pi minus infinity to plus infinity x tau by t minus tau d tau. Inverse Hilbert transform is defined as xt equal to minus 1 by pi minus infinity to plus infinity xh tau by t minus tau d tau. Now we have to prove that if we change every frequency component of xt by a phase shift of pi by 2, then we should get the Hilbert transform. For that, consider this model. We have h omega transfer function. Here we have xt, frequency domain is x omega. Here we have xht, frequency domain is xh omega. Magnitude spectrum is this. And phase spectrum is this. Now transfer function h omega can be written as h omega angle h omega, that is h omega e to the power j theta omega. Now here magnitude spectrum is 1. Since magnitude spectrum is 1, so this h omega magnitude is 1 into e to the power j theta omega, where this theta omega, if we consider this figure, theta omega equal to pi by 2 for omega less than 0 and minus pi by 2 for omega greater than 0. So h omega can be rewritten as e to the power j pi by 2 for omega less than 0 and e to the power minus j pi by 2 for omega greater than 0. Also, e to the power j pi by 2 is j, and e to the power minus j pi by 2 equal to minus j. So we can write h omega by j equal to 1 for omega less than 0, minus 1 for omega greater than 0. Or in other words, h omega equal to minus j signum function omega. The response xh omega of the phase shifted system can be written as x omega into h omega, that is equal to minus j x omega signum omega. Now if you take inverse Fourier transform in the both side, we will get xht, that is equal to minus j x omega signum of omega. Now we know that 1 by pi into t, its Fourier transform pair is signum function. So using time convolution theorem, we can write xht equal to 1 by pi xt convolution 1 by t, that is equal to 1 by pi minus infinity to plus infinity x tau t minus tau d tau. So that's the proof. That means to get this xht, we require a filter like this. We need a filter that will change all the frequency components of the signal by minus pi by 2. Then only we can get this xht, and after that we can get the corresponding SSB-SC signal.